The second part of this unit is going to be Chapter 11, which is Properties of Solutions, and this will be a bit of a review from the beginning of the year when we did solution stoichiometry, but we will go into it a little bit more extensively. Again, lots of definitions in this unit. Solutions, of course, are a homogeneous mixture, which can be gases, liquids, or solids. So sometimes students get caught up in that a solution is only a solid being dissolved in a liquid. But if you recall from Chem 1, you can have all kinds of solutions. Air is a solution, which is a mixture of gases. Alloys are solutions, which are mixtures of metals. There are three types of solutions. The first one is a saturated solution, and that is where the solution contains the maximum amount of solute that will dissolve under a given set of conditions. When you have a saturated solution, you are at equilibrium, which means that the same number of particles are dissolving that is recrystallizing, and it's happening at the same rate. The way that you know that a solution is saturated is you continue to add solute to it, and then when you see a few of crystals not dissolved at the bottom, then you know that you have reached the saturation point because no more will dissolve. The unsaturated solution, of course, is containing less than the maximum. And so as long as it will keep dissolving, then it is an unsaturated solution. And then the last type is a supersaturated solution. And it is a solution that you have to prepare it by heating it up and cooling it down. And then it contains more than it should at that given temperature. A saturated solution, or excuse me, a supersaturated solution is very unstable. If you add a seed crystal to it, it will cause all the excess solute to crystallize out. It would remain saturated when it was done. A good example of this is how we make sweet tea. We heat up the water, we boil the water, and then we add the sugar to it, and then we cool it back down and make iced tea. And so iced tea would be a supersaturated solution. A lot of times if you were to leave that iced tea, especially if you're like my aunt who makes it super sweet, if you were to leave it for a long time in the refrigerator or whatnot, a lot of times you'll come back after a vacation or something, there'll be this big, huge layer of sugar at the bottom because it has crystallized out. It's also how they make rock candy. If you were interested, you can make rock candy at home. It's very easy. Take a cup of water, heat it up, dissolve about 2.5 cups of sugar in it, maybe put a little flavoring in it, and then put a string, coat it in sugar once it cools down, and it'll grow crystals for you. So here we have a visual of the three. An unsaturated solution means I could keep dissolving. When no more solute dissolves, that's a saturated solution. Think about when you go to a restaurant and you order tea and you try to put sugar in it and it's already iced, and you stir and you stir and you stir and you have a bunch of sugar left at the bottom. That would be because that has reached its saturation point at that given temperature. And then, of course, super saturated was how we discussed on making sweet tea. Heat it up, dissolve it, and then cool it back down. A saturated solution, we'll say again, is at equilibrium. Next semester, equilibrium is going to be a huge topic for us, and we will be talking about solution equilibrium as well. And that is, of course, when the solute is dissolving and recrystallizing at the same rate. So it looks like nothing's going on in a dynamic equilibrium, but in fact it is. It's just happening on the particulate level. Here's an example of going from unsaturated to saturated, heating it up, going to supersaturated, and then whenever it cools back down and you have a seed crystal, it goes back to saturated. Units of solution concentration, you're in luck. We no longer have to do molality. We used to because of colligative properties, and colligative properties are no longer tested on the AP exam. I will mention them in passing, but colligative properties are those things that it does not matter what it is, it matters how much of it you have. Things like freezing point elevation and boiling point depression, and we don't have to do that anymore on the AP exam. They don't ask for that. So we have to know molarity, though. Of course, you remember that molarity is moles of solute per liters of solution. And, of course, we have to remember that whole solution stoichiometry where we do volume times molarity gives us the moles of solution. So you might want to recall how we did that in the beginning of the year. Mole fraction we also did in the beginning of the year, and it's coming back. And of course, that is the ratio of the number of moles of a given component to the total number. So we have your number of moles over the total number of moles, and that's your mole fraction. So here we have hydrogen sulfide gas as an example, has a solubility of 0.385 grams per 100 milliliters of water. And this, of course, at these conditions of 20 degrees and 1 atmosphere. We want to calculate the mole fraction of both the solute and the solvent in a saturated solution. So here we have, if we are assuming 100 milliliters, then our volume is going to be negligible because the density of water is 1 gram per milliliter. And then we have this hydrogen sulfide gas. If we divide by its molar mass, we get that we have 0.0113 moles. 100 grams of water divided by its molar mass means that we have 5.55 moles of water. You might want to pause the video if you're trying to catch up with my talking, so you can write that down. And then, of course, the mole fraction for hydrogen sulfide, that's that funny looking S, chi. We take the moles of hydrogen sulfide and we divide by the total number of moles, which would give our mole fraction of 0.00203. And then, of course, for water, we would take 5.55 divided by the total, and we get 0.998. This shows you that the highest percentage of this solution, of course, is the water. Again, pause the video if you're trying to catch up with my talking and your writing. So, the energies involved in solution formation. Whether or not the solute dissolves in a solvent depends on the strengths of 3 different attractions, and you should be prepared to discuss them. The first attraction, of course, is the solute particles for each other. How easy is it to break it apart? The attraction of the solvent particles for each other. How easy is it to break apart the water, if that's the solvent you're talking about? And then, of course, the attraction for the solute particles with the solvent. In other words, will it hydrate or surround it if it's water? The 3 attractions add up to give the overall heat of solution. So here is what that process looks like. I'm going to dissolve some sodium chloride, and then I've got to break apart the water, and then the water surrounds each different molecule, each different atom, and of course it orients it in the correct way possible. So we need to look at that. We drew that in our notes when we practiced the other day. First things, when we're drawing a particular diagram, you want to draw your anion larger than your cation. You want to draw them in the appropriate ratio. In this case, sodium chloride is 1 of each ion. The example we did in the notes the other day, I believe, was magnesium chloride. Excuse me. And so we needed 2 chlorines for every magnesium. So make sure when you're representing that, you do that in that manner. Also, whenever you're surrounding it with water, surround with a minimum of 4. 6 is better. This has 4. And of course, you want to orient the water where you have the positive side of water next to the chlorine or the negative anion, and you want to have the negative side of water oriented towards the positive sodium or the cation. Like dissolves like is something we said in Chem 1. In other words, polar dissolves polar, nonpolar dissolves nonpolar, and then, of course, ionic can dissolve in polar. This is a general observation to help you know what's going on. Do not ever state this as the reason. Do not say like dissolves like. You will not get credit for it. It's kind of like when we were doing the periodic trends, we couldn't say, oh, the periodic trend says it gets smaller as it goes across the period. We cannot say that. That is a general observation. Do not ever use it as an example. It's substances with similar types of intermolecular forces can dissolve in each other. Polar solvents dissolve polar and ionic. Nonpolar solvents dissolve nonpolar solutes. Water dissolves many salts because the strong ion-dipole attraction that water forms with the ions are very similar to the strong attraction between the ions. Okay, so remember, salts are ionic, so you want to write this down. You want to, or highlight it. This is what you would say in why can water dissolve sodium chloride or magnesium chloride, and that's because they develop a strong ion-dipole attraction between the water and the ions. The same salts are insoluble in hexane because hexane is nonpolar, and that's because the weak London dispersion forces that their ions could form with the nonpolar solvent are much weaker than the attraction between the ions. So the reason that a nonpolar substance will not dissolve something that is ionic or polar is not because like dissolves like. It's because the attraction for the ions in an ionic compound is stronger than any bond that would be able, or any intermolecular force, excuse me, not bond. It's stronger than any intermolecular force that it could form with the nonpolar solvent. Okay, so that's what you need to say. Oil does not dissolve in water because the London dispersion dipole forces are much weaker than the hydrogen bonding that's available in water. Okay, so these are the reasons these things will not dissolve. Please do not say like dissolves like. I've said that 3 times. So if I see that on a test, if you say like dissolves like, I'm going to fuss at you. Solubilities of alcohols in water. Remember, alcohols are those ones that have an OH on the end of something. And so as your hydrocarbon chains increase in length, the alcohol becomes less soluble. So I want to kind of show you an example. We have methanol, which would be COH, and then it's got the H's surrounding it. And then we have ethanol, which would be CH3, C2OH, and then the OH over here, and of course it has some more hydrogens. So you can see, oh, I drew too many, I'm sorry. Let me erase that. Oops, that should have been, whoops, that's not the eraser. Sorry about that. It's getting ahead of myself. Then the OH. And then of course you can get hexanol, which would have 6 of those carbons in a chain, and then the OH on the end. And so you could see how OH over here. So you can see how as it gets longer, becomes less soluble, and that's because more of that molecule, in this case here, would be considered nonpolar. And so as the chain of the alcohol gets longer, its solubility decreases in water, but it actually would increase in hexane or some other similar nonpolar solvent. So that brings us to that heat of solution that we talked about earlier. Remember, there's 3 things. You have the attraction of the solute for each other, the attraction for the solvent to each other, and then the attraction between the solute and the solvent itself. Okay, so we're going to talk about the heat of solution being a 3-step process. Delta H of solution can be positive, endothermic, or negative. So that delta H is coming back. So the first one is step 1, and that's breaking up that solute. It is going to be endothermic. It's called expanding the solute, okay? And the reason it's endothermic is it's going to take energy to break it apart because it doesn't want to break apart on its own, the bonds that are there. So it's called expanding the solute. And in ionic compounds and polar solutes, it's very high. In nonpolar solutes, it is a low number, okay? And it is equal to the negative of the lattice energy. Breaking up the solvent is also endothermic, and it's called expanding the solvent. Again, high in polar solvents and low in nonpolar solvents. And there's not really any ionic solvents that we're going to be using, so you don't really need to know anything about ionic solvents. And then the step 3 is the interaction of the solute and the solvent, and it tends to be exothermic. Again, it's very high in it's a high negative in polar to polar, and it's low negative in the rest. So then we have the enthalpy of hydration, and it is more negative for small ions and highly charged ions. And why would that be? Because they would have stronger Coulombic attractions if they're very small or very highly charged. So here we have step 1, step 2, and step 3. And then together they make up the delta H of solution. So delta H of expanding the solute plus expanding the solvent, and then plus the solution itself makes your heat of solution. So most of the heat of solution are positive, endothermic. And the reason for that is the solute dissolves, the solute that is doing the dissolve, excuse me, it's Monday morning, I'm sorry. The reason that the solute dissolves is that the solution process usually increases entropy or disorder. And you probably talked about entropy in physics. We haven't talked about it much in here. We will talk about it extensively when we get to thermodynamics. And of course, entropy is the disorder of the system. And if it is thermodynamically favorable, if it increases the entropy. The solution process involves two factors. And they are the change in heat and change in entropy, and of course their relative size. And that determines whether a solute will dissolve in a solvent. Factors affecting the solubility, the first one is going to be its molecular structure. Fat-soluble vitamins, for instance, are going to be able to go into your body tissue, your fat in the body tissue. There are certain vitamins that only will dissolve in fat. And then there's water-soluble vitamins, such as vitamin B and vitamin C. They are polar and they are not stored, so they must be consumed regularly. I don't know if you've ever taken a supplement that's really, really high in vitamin C. If you have, you probably got a surprise when you went to the restroom and your urine turned bright neon yellow, and that is because your body can't store vitamin C, so it just basically eliminates the extra whenever you go to the restroom. Then there's hydrophobic and hydrophilic. Those are two definitions you need to know. Of course, you know, if you have a phobia, you fear something, so that helps you remember that it's water fearing. And so that would be something that's nonpolar. And then hydrophilic is something that is water-loving or polar. Pressure affects the solubility of a gas with higher pressure. Pressure does not have any effect on the solubilities of liquids and solids, but it has a huge effect on the solubilities of gas in a liquid. With increased pressure, that solubility increases. That is something known as Henry's law, and that is the amount of gas dissolved in a solution is directly proportional to the pressure above the gas, above the solution. And so if you, I'm sure when you've had a soda, you open it up and you hear that psh sound, and that is the releasing of that pressure. The reason that the CO2 will stay in the carbonated beverage is because they have to put pressure on top. That's why after you open it, it tends to go flat because there's no longer pressure keeping that gas dissolved into the liquid. So here is an example, and you should see how as you push the piston down, you get more particles to be able to dissolve in the solution. Henry's law is obeyed best for dilute solutions of gases that don't dissociate or react with the solvent. Because, of course, if it's dissociating, such as, let's say, hydrogen chloride gas, when I put it into a solution of water, it becomes hydrochloric acid, and that's because those particles break apart and are being hydrated by the water. Temperature affects, of course, how much solute is dissolved. It usually increases with increasing temperature, but not always. Sometimes it may decrease. The solubility generally increases if the solution process is endothermic. In other words, a lot of your nitrates, when you put them in water, they get really cold. They feel really cold because it's an endothermic process. And so as you increase the temperature, you can get more of that solute to dissolve. But the solubility generally decreases if the solution process is exothermic. One example of that is sodium hydroxide, because it's very exothermic process. When I make up sodium hydroxide solution, it gets very, very warm. And if I were to heat up the water and try to put more sodium hydroxide in there, it actually has a counter effect. It actually would go down. Potassium hydroxide is another example. Sodium sulfate are three compounds that become less soluble as the temperature rises. And that can be explained by LeChatelier's principle. We briefly touched on that in Chem 1. We will touch on it a lot when we get to the equilibrium units next semester. Basically, LeChatelier's principle states that a system undergoing stress will adjust or shift in order to minimize that stress. The solubility of a gas in a liquid always decreases with increasing temperature. That's a problem in our waterways. When our waterways get too warm, the amount of dissolved oxygen that's in the waterways decreases, which is bad for the marine life because they are taking the dissolved oxygen out of the water. And so that's why sometimes if waters get too warm, you get a big fish kill floating to the surface because there's not enough oxygen in the water for them to utilize. Here's an example of some gases and how their solubility goes remarkably down as the temperature increases. Vapor pressure lowering is it's one of those colligative properties, but you do need to be aware that the presence of a volatile solute increases the vapor pressure. So the presence of a non-volatile solute lowers the vapor pressure. This is because the dissolved solute decreases the number of solvent molecules per unit. Non-volatile solutes dilutes the solution, basically, and there are fewer molecules on the surface to be able to escape to a gas. And here's an example of that. We have water, and then we have an aqueous solution, so we have things dissolved in the water, and less of that will have the ability to evaporate because of that non-volatile solute. Here's another example of that. See how the vapor pressure on the little monitor went down when I dissolved something in there. Another type of solutions are liquid-liquid solutions. And that is where both the solute and the solvent are liquid. Rubbing alcohol would be an example of that, the kind you put on your cuts and scrapes. It's 70% by volume, so 70% alcohol and water, the rest of that. And if the solute is more volatile than the solvent, the vapor pressure of the solution is higher. So that's a very good example of the vapor pressure being higher. Alcohol evaporates much more quickly than water, even though that does have water present in the solution. So here we have solution A, solution B, and then I mix them together and the vapor pressure increases, meaning it becomes a gas more readily. And I believe we're going to stop here. This is a long enough lesson. We'll continue tomorrow.